So my name is Omri. Great to be here. I love to be in the Foresight events. My day job is a general partner at a fund called NFX. We manage 1.4 billion. Our sweet spot is kind of $2 to $5 million lead checks at the seed stage. 5 partners under one focus on intersection of tech and bio. But today I'm going to talk about one of our companies called Renewal Bio, which is kind of mind-blowing, and I'll tell you all about it. So we love longevity. If you go to nfx.com/bio, we wrote about it. We have a book about it, a video, a movie about it. But again, the best technology I ever seen is the technology behind this company that was discovered by Professor Yaakov Chana from the Weizmann Institute in Israel. And I have a short 1-minute video about it.
Human embryos created entirely out of lab-grown stem cells. No sperm or egg required.
For the first time, successfully creating a viable synthetic mouse embryo. And they did it with nothing but the mouse's own skin cells. It's projecting that within 5 years, we'll be able to take a patient's skin cells, revert them to stem cells in an already developed device, and then within a few weeks, produce any needed transplant material that is genetically identical to the original patient.
Scientists say it will allow them to understand more about those early stages, a widely understudied topic and one that could be helpful for humans.
Grow them in special condition and put them in this device for about 20 days, and they self-organize alone over 8 days into a whole embryo. And we can take these cells maybe and transplant them back to the patient.
Yep. So everything I'm going to show you today was peer-reviewed, published, and I'm going to show you some unpublished result in the end. The mouse data was published on the cover of Cell 2 years ago. You can see that this is not the embryo you were looking for. And on the right, it's the human data that was published on the cover of Nature last year. What you see here is day 14 human embryos made out of stem cells. So maybe I shouldn't call them embryos. The right name is stembroid or stem cell derived embryo models, because we want to be careful with the way we name it. The notion behind this entire story, or the notion of replacement, is that nature solved aging, right? If you think about it, older men, 70, 60 years old with older cells can have a baby with a 40-year-old woman with 40-year-old cells, and that baby has a 0-year-old cells, right? There is something magical that nature developed, otherwise we won't be here, that can refresh lifespan if you go through one cell onward. In human, we solve the aging for things like our cars, right? How do we do it? A combination of maintenance, but mainly replacement. And the thing I like about replacement is you don't have to understand aging, you don't have to stop aging. You just need to figure out a way to find young, genetically identical replacement part and just keep replacing. So the story started about 10 years ago at MIT. Professor Yaakov Chana developed this. Calling it artificial womb is kind of too much. It's a bioreactor he used to grow embryos outside of the uterus. Initially used it to take natural mouse embryos and grow them from 0 days, which is a ball of stem cells, to day 13 and a half out of 20. So 2/3 of pregnancy was captured outside of the uterus. And he used this model published in Nature to study a lot of the early developmental stages. But once we had the conditions we need to have and we have the hardware, the next step, and I think this is what is going to win the Nobel Prize, is getting embryos directly from stem cells. So no sperm, no egg, no uterus. So what he did, that's on the cover of Cell 2 years ago, was take naive stem cells, split them to 3 populations. One in red, he pushed to become the placenta. In green, he pushed that population to become the yolk sac. In blue, he kept them as naive stem cells. Co-aggregate 25 cells in mouse, 120 in human. Let them grow for a few days, move them to this artificial uterus, if you want to call it. And some of them became up to day 8.5 embryos from stem cells, synthetic embryos, which is kind of mind-blowing, almost half pregnancy. What you see here is a movie from that paper showing the same system I showed you before, but this time growing synthetic embryos. So this is a bunch of mouse clones, in a sense, just floating around. This is a yolk sac expanding, and we can make as many of them as we want. So we start with 25 cells, let them grow for 3 days. After 3 days, you start to see the asymmetry developing, and then day 4, 5, 6, day 7, the yolk sac expand. Day 8, you can see the embryo growing inside of the yolk sac. This is a movie of one of them. You can see the heart beating down below. Again, embryos just from stem cells. And the unique thing about this technology, this is the most technical thing I'll show you today. This is a plot of single embryo, single cell RNA sequencing. This is a control. Natural mouse embryos grown inside of the uterus. And this is 5 synthetic embryos. And what it shows you that we have all the cells we expect to have. We don't see any UFO cells. And the similarity is more than 95%. Actually, for the embryo, it's more than 99%. And people tell us, what you're doing is great, but why not go directly from induced pluripotent stem cells and get whatever cell population that you want? The problem is, we've been trying to do it for more than 20 years. There are very few cell types we can differentiate from stem cells. And those cells, if you do RNA-seq, look nothing like natural cells. So when that paper was published, it went all over the news because it's kind of mind-blowing. You could read it in New York Times, CNN, etc. And the question was, can you do it in humans? And that was a paper we published in Nature last year. What you see below is a picture from a textbook of development. That's how human embryos should be developing until 14 days. This is our result from the paper, one-to-one, with all the cell types, all the structure you expect to see at that stage. Here you see in this video, this is a scan of one of the human embryos at day 14. We even went to CVS, got a pregnancy test, and the embryos are so natural that at day 8, it's already triggering the pregnancy test. So it's alive. And you can see those structures like the biliminar disc and other structure you expect to see. So we haven't stopped there. Started a company, raised more than $9 million. We 10x the yield from the first paper. Unpublished data, but we already got to day 21. The paper in Nature was day 14 from embryonic stem cells. This is day 21 from iPS, include GMP iPS. So I can take adult person, natural cells, again, no sperm, no egg, just not skin because too much mutation, but let's say blood cells, turn them into iPS, turn them into naive iPS, turn them into synthetic embryos, and get a bunch of young, genetically identical everything in an ethical way. So our first milestone is getting to day 28. We can get fetal liver hematopoietic stem cells. And there's a bunch of diseases we can potentially cure, but also what will happen if we can get our own young, genetically identical bone marrow? Will we get in a new immune system, for example? And a lot of age-related disease happen when we grow older, our immune system starts to decay, we get a bunch of diseases. So that's kind of the first, low-hanging fruit. Day 40, we start to get hepatocyte for liver diseases. We get brain tissue for potential for stroke or other indication. At day 70, we get gonads. Potentially, we can produce eggs. So as many eggs whenever you want, including potentially male-derived eggs. That's a whole new thing we potentially can do. Ovaries to potentially delay menopause, insulin-producing beta cells, and then currently, the equivalent to the phase we can grow mouse embryos, day 13.5, is day 88 in humans. And we need to solve technical issue and an ethical issue. The technical issue is currently we're feeding the embryos through diffusion. This is mice work. We got in mice to day 13.5. After that, they stopped growing because we cannot feed them. So initial work we've done in mice is because we have a placenta, can we collate and start feeding them through the placenta to potentially grow them for further stages? And on the ethical side, it seems like everybody is fine with day 14. Actually, even the Christians here in the US are fine. They said, look, we believe life begins in conception, and there is no conception, so we are okay with technicality. I'll take that technicality, it's fine. But we are not fine with 9 months, if we can get there, right? So there is an ethical line we need to be aware of. In mice, we did this experiment where we did a translate experiment of CRISPR-LIM1 gene. LIM1 is a transcription factor responsible for brain development, so we got this synthetic mouse embryo growing without a brain. But the idea is we have real indication we can go after. It's a longevity company, but we can cure real diseases. We have a bunch of IP around it. We have the team from Jakob Hana Lab that is working very hard right now as we speak. And I think this is one of the few technologies that can really move the needle in longevity for all of our futures. So thank you very much. Questions?
Hey, Omri. So when can you shut up and take my money?
Now.
Okay, let's go have
No, you should talk.
No, seriously.
When,
The good thing about being at NFX, a fund, being a partner at the fund, that I could fund my own companies. So we did the pre-seed ourselves, and we let the seed. We put our money where our mouth is. We already invested 6.2 million in
Oh,
this.
sorry, I wouldn't mind investing, but I meant when can I buy the organs that I need?
Well, you can give us some of your cells, and we make as much embryos as you want. But currently only to day 21, and I don't know how helpful it will be. Like you want at least day 28 to start doing bone marrow transplant, and even then, obviously, we have to go to the FDA and all this stage.
one question from Ravi.
So it looks like you're planning on using some of the cells from the embryo. How are those better, worse, different from just taking the iPSCs and then creating different?
Yeah, that's a common question, right? Why create an embryo to take cells? Why can you go directly from iPS to cells? So first of all, there's a company called Garuda. They raised around $200 million trying to get HSCs from iPS. They couldn't do it so far. And if you look at, there are very few lineages we can differentiate properly from iPS. And even then, if you do RNA sequencing, they look nothing like natural cells. Because again, think about development. We are riding on the coattails of 4 billion years of development and evolution, right? The magic of our platform is create the embryos. Everything else, we just feed them. And everything just happened by itself. Like the embryo knows how to secrete all these different molecules in the right place in the right time to get the perfect cells, perfect organs, right? Nature doesn't know how to make a heart. Nature doesn't know how to make HSC. It knows how to make an embryo that makes a heart, right? That's a natural way. People are trying to print or whatever. It doesn't work. That's the only way to get those cell types. I wish there was a cheaper, better, faster way. Now, how do we get those cells? For HSCs, we need to grow a machine worth of embryo. We dissociate them and filter for CD34 cells, and we have a therapeutic dose. For eggs, you only need one embryo because each embryo has millions of eggs. So, it depends on your indication, depends on what you want. For HSC, we potentially can create a universal donor strain, so we can have off the shelf. For eggs, I don't think anybody wants universal eggs. But, yeah.
Thank you so much.
Okay.